Alright, welcome to video 9.5. So this is a kind of just an additional commentary to the nonlinear prediction error method. So we saw here that we made use of a model that has a dynamics function f, and then it has some noise disturbing the evolution of the state. This noise can be viewed as either some disturbance, for instance, sun shining in through your window, or there is a wind blowing on your aircraft or something like that. But it can also be interpreted as a model error. So if this is a fixed structure model, maybe we have forgot to model some physical phenomena. If we have a quad rotor, maybe we have forgotten to model the ground effect or something like that. Or if it's a mechanical system, maybe we didn't model the friction very accurately, and then we can say that this model error is captured by this term here. All right, so given a particular predictor, we will try to predict the output given the past outputs and inputs. But I said before that when we optimize prediction error performance, we get a good predictor, but we might not necessarily get a good simulator. So if we have some notion of physical significance of these parameters, maybe our predictor will find parameters that allow us to predict data very well, but the parameters don't correspond to what we believe to be the true parameters of the system, or maybe the simulation performance of the model is not very good when we have optimized the prediction error performance. And we saw that when we set the initial guess to be very poor, we get a poor simulator model, but we get the predictor model was still good. All right, so when we use a Kalman filter, the Kalman filter will take the covariance properties of the W and the E, and compute the optimal K to adjust the state with. And if we say that the covariance of W is very small, but the covariance of V is very large, so that means that our measurements are bad, but the model is good. And then the Kalman filter will come up with a very small K. Okay, so it will say that, yeah, we shouldn't trust the measurements, we should instead trust the model more. So therefore this K should be small. We make a very small correction based on the measurement. But if we go in the other direction and say that the measurements are very good, but we have a large error in our model, then the Kalman filter will make a lot of use of the measurements. All right, so it will perform less filtering if we want, and rely more on the data. And for a nonlinear system, that's slightly more complicated, but for instance, an uncentered Kalman filter will internally compute a K based on the covariance properties of W and E. So if we let the covariance of this E here, we specify that ourselves. If we let that go to infinity, then the larger we make that covariance, the less the predictor will make use of the data. So in the limit of infinite measurement covariance, we kind of approach the simulation model. So a model that doesn't make use of any past measurements at all. So if we have obtained a poor simulator when we estimated using prediction error method, one approach is to initially solve a prediction error optimization problem with a reasonable sized covariance for both of those. And then we determine, okay, this model is not a very good simulator. Then we can kind of solve an additional problem, a second problem, where we artificially increase the covariance of the measurement noise. And then the predictor will be forced to find a better simulator. All right. So for the linear case, we don't care about the absolute values of the covariance matrices, rather it's the ratio between them that matters. For a nonlinear system, it's not that simple. The absolute values actually do matter. So it's a bit more difficult, but the same overall kind of conclusion can still be made, that if we make the covariance of E very large, the predictor will ignore the measurement. So that's a nice kind of trick we can apply if we are struggling with finding a good model. All right, thank you.